Let's talk about the fundamental theorem of calculus. Now, this is a big theorem in this course. I mean, it's fundamental. So this video is really just going to deal with a warm-up to prepare us to understand and prove the fundamental theorem of calculus, all right? So the first thing I want to do is I want you to recall the mean value theorem. Now, the mean value theorem had two conditions. So these two things are conditions. The first condition was that we need f to be continuous on this closed interval from a to b, okay? The second condition that we had was that we need f to be differentiable on the open interval from a to b. And if both of these conditions are satisfied, then we have a conclusion. And our conclusion was that there exists a C in your open interval AB such that f prime of C is equal to f of B minus f of A divided by B minus A. In other words, this thing on the right-hand side looks like a slope. This is the slope of the secant line. And this theorem basically says there's some point inside the interval that has the same slope as the slope of the secant line. So what we really need to do is we really need to take this idea and modify it slightly to create a mean value theorem for integrals. So again, if f is continuous on a closed interval from a to b, then there exists a c in the open interval from a to b such that the following is true. You will be able to find a c so that f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. Okay, now this integral on the right-hand side right here, this is known as the average value of a function from a to b, or let's say on a to b. Okay, so if you were to look at this, you know how you find the average of a bunch of numbers, you add them all up and then divide by the total number of numbers. In this case, instead of adding all the numbers up, we're basically finding the area under the curve. And instead of dividing by the number of numbers, we're dividing by the length of the interval that you integrated over. All right, so this mean value theorem for integrals says if you have the average value of a function, there is some point C that attains the average value of a function. In fact, I'm going to write that down. This says f attains the average value of a function at some point C in AB. Okay, so the reason why I need to tell you this mean value theorem for integrals is we use this theorem in our proof for the first part of the fundamental theorem of calculus. So I also want to tell you about a new type of function. So let me highlight this new function for you. So capital F of x is going to be defined to be a function that looks like this. You have some other function, little f, and you're going to integrate from a to whatever x is. So the idea is that the variable is in the upper limit of integration. Okay, so the variable is the upper limit of integration. And it's really easier to look at this and look at a few examples. So I want you to take a look at this graph that I have on the left-hand side over here. This graph is kind of playing the role of little f. So I'm going to say little f of x, this graph is equal to the constant function 2. Okay, and the capital F that we want to study looks something like this. So our capital F of x is going to be the integral from 0 to x of the function 2 dt. Now this variable of integration needs to be a different letter than the upper limit of integration, because the upper limit of integration is my independent variable. So this is what we call like a dummy variable. Okay, so why don't we look at a few examples? So what would capital F of 1 be? Well, that would be the integral from 0 to 1 of 2 dt. And if I were to shade that in over here, basically what we would get is we would get a rectangular box. So let me shade that in blue over here like this. And I hope you can see that the height of the box is 2 and the width of the box is 1. So 2 times 1 is equal to 2. What if we looked at f of 2? What would that look like? Well, in that case, we would just integrate from 0 to 2, the constant function 2 dt. So in this scenario, I'm going to erase this this line here, and I'm going to move it all the way to 2 like this. And then I'm going to calculate this new shaded area here. Okay. And when we do that, what are we going to get? Well, the height of the box is 2. The width of the box is also 2. 2 times 2 is 4. So that area is going to be 4. Let's look at one more example. Let's calculate what f of 3 is going to be. In that case, I'll just integrate from 0 to 3 to dt. And I think you could probably guess what's going to happen here, but let's just do it real quick. So if I erase this, and then I've now put my line at 3, and I want to find the area under this box. The area under that box is this whole blue shaded area. This time the height of the box is 2, but the width is 3. 2 times 3 is equal to 6. Okay. Each of these independent variables were chosen to be whole numbers, but you could really have any number, any real number here, and you could still calculate the area quite easily. So maybe this example looks a little too simple for you, so let's take a look at this picture on the right-hand side. So when I look at this function, let me call this function, just to give it a different name, we'll call it g of x. So g of x is going to be equal to the integral from 0 to x. And when I look at this function is a line, right? This is going to be small g of x equal to 1/2 x. How do I know it's 1/2 x? When I look at the slope of this line, the slope of this line is equal to 1/2. And in other words, for every 2 I go over, I go up 1. And the y-intercept is the origin. So this is the equation of a line. All right. So I have to introduce the dummy variable because x is used for my upper limit of integration. So the integrand is going to be 1/2 t dt like that. Okay, So let's calculate g of 2. In this case, I should integrate from 0 to 2, 1/2 t dt. So let me draw a picture of what we're doing. I'm going to draw a little line here at x equal to 2. And we're going to shade that area under the curve from 0 to 2. So we're really calculating the area of this red triangle right here. Okay, so that's going to be equal to 1/2 the base times the height. So that's going to be equal to 1/2. The base has length 2, the height has length 1. That total area is going to be 1. Let's calculate g of 4 next. So in this case, we're going to integrate from 0 to 4, 1/2 t dt. So I'm going to come over here. I'm going to erase my little line. I'm going to go all the way to 4 and let me shade all of that area. So we're going to find this red area under the curve there. Okay, so I'm going to use the formula for the area of a triangle again. This is going to be 1/2. In this case, our base is 4 and our height is 2. So when we simplify, we're going to get an answer of 4. So these would be like 4, units squared or whatever. Okay, so the purpose of this video is just to set up things so you actually understand what we're talking about when we look at the fundamental theorem of calculus. There's going to be 2 parts to it, and the first part really works with functions of this form. So I really wanted to just give you a feel for what it looks like with a couple of examples. All right, everyone, take care.